Hi. In this video, what I'm going to do is I'm going to talk about the second part of chapter 15, which is chemical equilibrium. In the previous video, we looked at how we write expressions for the equilibrium constant, Kc, where C stands for concentration, and Kp, where P stands for pressure. For gases, we typically use Kp, and for aqueous solutions, we typically use Kc. Now what we're going to do is we're going to start getting into the calculations, calculating the equilibrium constant. Okay, the first type of calculation is rather simple, but it will very quickly become more involved and we'll start having to use some algebra to solve these problems. So let me bring up a problem here for us to take a look at. This is called calculating an equilibrium constant from an equilibrium composition. So the point of this calculation is they're going to tell us what the equilibrium concentrations or pressures are, right? Composition here. So this is going to be different than the other problems that we're going to do here, but this one, they're telling us what these pressures are at equilibrium. So when you read these problems, make sure you first see, is it at equilibrium? And here it's saying that it is. So let's read the question. Hydrogen and chlorine react to form hydrogen chloride like this. H2 gas plus Cl2 gas to form 2HCl gas. Now, one thing that I would say about the expression here is that they're not using the double arrow, and they probably should. It should be a double arrow here. This is an equilibrium problem, so we would put the double arrow there. Also, a chemist finds that at a certain temperature, the equilibrium mixture of hydrogen chloride and hydrogen chloride has the following composition. H2 is at 56.3 atmospheres, Cl2 is at 10.3 atmospheres, and HCl is at 70.3 atmospheres. These are equilibrium pressures, and that's key to this. It makes it a very easy problem. So what we want to do is we want to calculate the value of the equilibrium constant Kp for the reaction and round it to 2 significant digits. Typically, equilibrium constants are not known to more than 2 significant digits, occasionally 3, but typically 2. Okay. So here's our balanced equation. It is balanced. We have our equilibrium pressures, so we can calculate Kp. So let's go through it. Okay. So H2 plus Cl2 goes to 2HCl. Okay. We're going to try to calculate what Kp is. We are told the equilibrium pressures, so I'll just write them down here. E for equilibrium, 56.3 atmospheres, 10.3 atmospheres, and 70.3 atmospheres. So that's at equilibrium. Okay, let's write the expression first. Remember, we learned how to do that in the previous video. Kp means we're going to do pressures. So it's going to be the pressure of we do the products first. HCl squared, products over reactants, pressure of H2 times the pressure of Cl2. Right? I'm not going to write any symbols for multiplication, but when we see 2 P's in there, that means you're multiplying them together. So as long as we have the equilibrium pressures, we can calculate those very easily. We just substitute in our values. So this would be 70.3 squared, right? This is to the second power because of that 2 divided by the pressure of H2, 56.3. And then Cl2 is 10.3. Those are both to the first power because the coefficients are 1 in each case. Okay. Now we can go ahead and calculate that. Let me take a look here. I'm going to take 70.3 and I'm going to square it. And then I'm going to divide that by 56.3. And then we're going to divide it by 10.3. And it looks like it comes out to about 8.5. That's at 2 significant digits, about 8.5. Okay. So they get relatively simple. As long as we know what the equilibrium pressures are, we can do that calculation. Okay. Let's bring up another one. Let's see if it's any different. Okay, here's one. Calculating an equilibrium constant from an equilibrium composition again. Nitrogen monoxide and hydrogen react to form nitrogen and water like this. So 2NO plus 2H2 forms N2 and 2H2. They're all gases, so we can do Kp. Also, a chemist finds that at a certain temperature, the equilibrium mixture of nitrogen monoxide, hydrogen, nitrogen, and water has the following composition. So these are all at equilibrium. Calculate the value of the equilibrium constant Kp for this reaction, okay? All right, so let's try this one. Okay, we have 2NO. 2H2. Okay, remember, this is equilibrium, so it should be a double arrow. N2 gas plus 2H2O gas. Okay, this is all at equilibrium, so I'm going to put an E here for equilibrium. So the NO is at 13.8. The H2 is at 90.7. The N2 is at 11.9. And the H2O is at 93.5. Okay, those are at equilibrium. So let's write the expression. Okay, the first product is N2, so pressure of N2. The coefficient is a 1. The second product is H2O. Remember, these are all gases, so we're going to put them all in here. If they were solids or liquids, that would be heterogeneous. We wouldn't include solids or liquids in this expression. Pressure of H2O. But now we're going to square it because there's a 2 in the coefficient. Divide that by the pressure of NO squared. Divide it by the pressure of H2 squared. Okay. Hopefully that makes sense. Now we can substitute in our numbers. So N2 is 11.9. Remember, for equilibrium constants, we do not include the units. We just get rid of all the units, just ignore them. Water is 93.5. We're going to square that. And then we're going to divide that by NO, which is 13.8. We're going to square that. And then H2 is 90.7. And that one we got to square also. Okay, so this calculation is a little bit more involved. So let's take a look. It's 11.9 times 93.5 squared divided by 13.8 squared divided by 90.7 squared. So we end up with 0.066, 2 significant digits, no units, okay? So when we report values of equilibrium constants, whether it be Kp or Kc, we're not going to include units in those results, okay? So hopefully that's pretty straightforward for you. Now, the problems very quickly become a little bit more complicated, but I'm going to show you a couple of more problems here. So let me bring this one up. Okay, so this is using the general properties of the equilibrium constants. So we're going to do a couple of little calculations here, but the first part of this question is going to be sort of a conceptual understanding. It says here at a certain temperature, the equilibrium constant K for the following reaction is 4.1 times 10 to the minus 6. Now they're not saying whether it's Kc or Kp. Typically, if it doesn't say either, it might be Kc. It's hard to say. It doesn't really matter for our problem here, though. The chemical equation is NO2 gas plus CO gas, so that's nitrogen dioxide plus carbon monoxide, are in equilibrium with nitrogen monoxide gas and carbon dioxide gas. Use this information to complete the following table. Suppose that 47 liters, okay, we're talking about gases here, so they're giving us volumes. Suppose that 47 liter reaction vessel is filled with 1.2 moles of NO and 1.2 moles of CO2. What can you say about the composition of the mixture in the vessel at equilibrium? So what they're saying is they're initially putting in this 47 liter container. It's a pretty big, good sized container. They're putting in 1.2 moles of NO and they're putting in 1.2 moles of CO. What can you say about equilibrium? And the answer is we don't have any results for equilibrium, but remember what we said about the power of the law of mass action or the power of the equilibrium constant, that it doesn't matter what our initial compositions are. Once it comes to equilibrium, there's going to be a mixture of reactants and products that will give us a value of K that doesn't change as long as we don't change the temperature, right? So as long as the temperature is constant, it doesn't matter what our initial amounts. If I'd taken 1.2 moles of this and 1.2 moles of that, I should end up with the same ratio here. Okay, the equilibrium constant is a constant. Look at what our options are. There will be very little NO2 and CO. There will be very little NO2 and CO, very little NO and CO2, or neither is true. Here's what we want to do. Look at the value of K. If K is a large number, more than 1, 10, 100, 1,000, 1,000,000, what that means is the ratio of the products divided by the reactants is large, okay? Because K is defined as products over reactants. So if you have a large value of K, that means there's a lot of products and a little bit of reactants. Now, if you get a value near 1, then it's like there's a mixture. But if you have a value much greater than 100, 1,000, that means there's a lot more products than there are reactants, or much less reactants than there are products. Make that ratio for yourself, products over reactants. On the other hand, if K is very small, this is a small number, right? This is a millionth, 4.1 millionths. If it's very small, that means that the ratio is small. So products over reactants is small. So that means that there's not very much products and there's more reactants. So we have a small value here, so not very much products. So what are the products? NO and CO2. So that means there will be very little NO and very little CO2. So it would be this option right here, the second one right here. Okay. Now, what is the equilibrium constant for the following reaction? Round your answer to 2 significant digits. Okay. Notice what they've done with the equation here. They've taken the one that's given here with this value of K, and they've flipped it. They reversed it is the more technical term. Everything that was a reactant is now a product. Everything that was a product is now a reactant. They reverse the equation. Now, if you think about how we deal with equilibrium constants, reversing the equation has the effect of changing what's on the denominator into the numerator and taking what's in the numerator and putting it into the denominator. Now there's a mathematical function for that, right? If you take 6 over 2 and I change it to 2 over 6, that's called taking the reciprocal, not the inverse. Don't call it inverse. It's the reciprocal. Reciprocal often referred to as 1 over x. So when we reverse an equation, the constant is just going to be the reciprocal of what it was initially. Okay. Now, in the third part of this question, take a look at what happens here. There's NO2 and CO are reactants. That's the same thing we have over here. NO and CO2 are products. That's exactly, so they didn't reverse the equation here. It's still this equation here, but they put 3's as coefficients in front of everything. They've changed the coefficients by multiplying by 3. Now, what's interesting about that mathematically is because we're multiplying things together and dividing by things together with the equilibrium expression, changing the equation by multiplying by 3 doesn't have the effect of tripling the concentrations in the equilibrium expression. It has the effect of changing the exponents by 3. Okay, so let me show you how to go about this one. It's kind of a fun question. It's a fun problem, actually. So I'm going to write the equation here. NO2. I won't put the states of matter just to save a little bit of time and space. Now I'm going to go ahead and write out the expression here as concentration of NO. I'm doing case C. You can do the same thing with KP. Okay. This piece of information is given here. There's our KP, KC. Okay. So the first part of the question is, will there be very little NO2 or very little NCO, or will there be very little NO and very little CO2? So there will be a little bit of this one or a little bit of this one. And the answer is, this is a small value. It's much less than 1. That means this right here is going to be much smaller than the denominator, right? The numerator has to be smaller than the denominator to get a number less than 1. So to be much less than 1, the numerator has to be much less than the denominator. Well, the numerator is NO and CO2, so this has got to be very small. Okay. Now, the next issue is they reverse the equation. Okay, so now we have NO plus CO2 goes to NO2 plus CO. That's the reverse. I reversed the equation up here to turn it into that. So here's what happens actually. What happens is when you reverse the equation, now the reactants become products and the reactants become products and the products become reactants, right? You reverse them. So you can see this is just the reciprocal. This right here is just the reciprocal of this. So I'm going to put a little prime there. I'm going to say that KC prime is just the reciprocal of KC. That's just that the little prime is just saying it's a different equation. It's 1 over. So all you got to do is just take 1 divided by 4.1 times 10 to the minus 6. That's all you got to do. Okay, so you put in your 4.1 times 10 to the minus 6, and then take 1 over x. That's called the reciprocal. And you're going to get a big number. It's going to be 2.4 times 10 to the 5. Okay, Kc prime, the Kc value for the reciprocal, okay, for the reverse reaction. So you don't have to go through writing an expression every time. You can just notice, oh yeah, this is the reversed equation. So all I got to do is take 1 over the k that was given, and that will give me my new one. Now the third one is 3NO2 plus 3CO goes to 3NO plus 3CO2, and we want to know k for this one. So I'll call it double prime. Okay, now let me show you what's going on here. It's the same equation as this one, just has 3's, but look what happens to the expression. Now all the coefficients are 3. So our exponents become 3. Isn't that cool? The exponents have become, so really, this is the same thing as our original KC. So I'm just writing out the original, the one at the top. And I'm cubing it, right? I'm not factoring out the cube. I'm just writing it separately, right? Because these are all multiplied and divided by, so you can just write the 3 outside. So this whole thing in the inside here is just KC. So that means our KC double prime is just KC cubed. So anytime you see that the equation, the original equation, has been multiplied by some value, you just take your original KC and you raise it to that same value. So if I'd multiplied, suppose it had been 2NO2. Well, then I would square it, right? So now your KC triple prime would just be KC squared, right? You just square it. So 4.1 times 10 to the minus 6 squared. That ain't right. 4.1 times 10 to the minus 6 squared. Ooh, it's a small number. It's 1.7 times 10 to the minus 2, 4, 6, 8, 10, 11. Okay, so there's your KC double prime. So there's the answer for the last one. Okay, so that's, they're kind of fun. There's really just 2 things. Now, you could combine them too. I could say I'm going to reverse the equation and multiply by some value, and that's perfectly fine. You can do that as well. Okay, I do want to point out that if you take an equation, so let's say my equation is this. And I'm going to make them all gases. Okay, and let's say this is KP. I'm going to make up a number, 3 times 10 to the 50. Okay, suppose that I divided everything by 2 or multiplied by half. So suppose I had H2 plus 1/2 O2 goes to H2O gas. Okay, so I've multiplied everything by half, right? So the way you would deal with that, how do you know I multiplied by half? What do you mean? I divided by 2, but dividing by 2 is the same as multiplying by half. We don't want to talk about in terms of division. We want to talk about in terms of multiplication. So if I multiply everything by half, right? What do we do to KP? We raise it to a half, right? Whatever I'm multiplying the equation by, that becomes the exponent, right? It was 3 in the previous example. Here it's going to be half. What does that mean when we say that we're going to raise something to the half? There's a notation for that. So if I say x to the half, that's the same thing as the square root of x. Okay, so this would just be the square root of our original KP. Okay, now what if I said, oh, I'm going to multiply it by 3/2? Now this is relatively rare. You're not likely to see that. What that means is you're taking it to the third power, right? And then you're taking the square root. So you raise it to the third power, then you take the square root. Okay, so same thing with that one. But it's unlikely that you're going to see it multiplied by 3/2. You might see it multiplied by half, but it's unlikely you'll see it multiplied by 3/2. Okay, so there's that problem. The next one I want to show you involves an interconversion. This is a pretty standard problem. It's not the kind of thing that you're probably going to do if you become a biochemist, but it is a pretty standard problem, and that's the interconversion of Kp and Kc. Consider the following chemical equilibrium. H2 plus CO2 goes to H2O and CO2 and CO, all gases. Write an equation that shows how to calculate Kc from Kp for this reaction at absolute value T. You can assume that T is comfortably above room temperature. If you include any physical constants in your equation, be sure to use their standard symbols found in the ALEKS calculator. Okay, so I'm going to go through a derivation. I don't do very many derivations in this course because they take up a lot of time, but I'm going to show you a derivation. So let me go through it. I'm going to use this particular problem as an example. And it looks like you don't have to actually do the calculation on this problem. They want you to write the formula out. So let me write this over here, H2. And this is all based on talking about a reaction where everything is a gas. Things get complicated if you have mixtures of states. Okay, so what I'm going to do is I'm going to write out two expressions. The first one is Kc. It's the concentration of H2O times the concentration of CO divided by the concentration of H2 divided by the concentration of CO2. There's your Kc. Okay. Now I'm going to write out the expression for Kp. I'll do that here. Pressure of H2O times pressure of CO divided by pressure of H2 divided by pressure of CO2. Okay. Makes sense, right? Kp, Kc, Kc, Kp. Can we convert between them? And here's how we can convert from them. When we're dealing with gases, we have the ideal gas law. I hope you remember that from Chem 11. PV equals nRT. Notice how there's pressure in this equation, and Kp is pressure, right? It's based on pressure anyways. So what I'm going to do is I'm going to divide both sides by V. And now I have P on the left side equals N over V times RT. Interestingly enough, okay? So what is N over V? N over V is moles over volume, right? Now, if volume is measured in liters, then we have moles over liters, and that's called molarity. And molarity, well, let me write it out, a molarity is a concentration unit, right? In fact, it's the concentration unit that we're using when we use the bracket notation, right? All of these materials, if we're dealing with concentration or that. So it's not unusual then to do it this way. We're going to say that pressure is equal to the concentration of the gas, N over V, times RT. Okay, so now for all four of those substances on the right here, I'm going to write this as pressure. Okay, pressure is the concentration of the gas, so that'd be the concentration of H2O times RT, right? This is called substitution. the pressure is equal to the concentration of the gas times RT. So since I have pressure of H2O, that would be the concentration of H2O times RT. That would be equal to P over here. And we're going to do the same thing for each one. So we have that times concentration of CO times RT. Right, so I'm doing the same thing here. I'm putting CO in here. Concentration of CO times RT is the P. Do the same thing down here. Pressure of H2 is the concentration of H2 times RT. Concentration of CO2 times RT. Now, what is R and T? R is the universal gas constant. T, temperature, right? In Kelvin. But look what happens. All these RTs cancel. And Kp, interestingly enough, is exactly the same as CO. I'm sorry, Kp is exactly the same as Kc. So Kp equals Kc. So the question says, write an equation that shows how to calculate Kc from Kp. Well, Kc equals Kp. And there's your, there's your equation that will show how that works. Now, here's the thing. It doesn't always work out so nicely. Sometimes the RTs don't cancel. So I'm going to show you another example here. Okay. Notice how this equation, same problem, we're going to show an equation, is NH4SH solid is in equilibrium with H2S gas plus NH3 gas. So in this particular example, there's a solid. Remember what we do with a solid? We just make it 1, right? So our Kp and Kc, we're just going to use 1 for that solid, but we'll work it out the same way. Let's work on this one. Let's do this one. Same idea. I'm going to start from scratch. This one really does kind of require you to go through it. Okay. Here we go. So I'm going to write the equation. And I'm going to do Kc first. Now that's divided by 1, but if we're dividing by 1, we can just leave the 1 out. We don't need to write it. So there's our Kc. Now let's do Kp. It's the pressure of H2S times the pressure of NH3. Again, divided by 1, we can just leave that out. Okay. Now, are they equal? Let's see. Here's what I'm going to do. Pressure of a gas is equal to the concentration of gas times RT, right? P equals nRT, so you divide both sides by V, so you get N over V, which is concentration. Concentration times RT is equal to P. So we got to do that for both of these gases, right? So for Kp over here, we're going to have concentration of the first gas, H2S, times RT, and then pressure of NH3 is the concentration of that gas, times RT. Now look what happens. The RTs don't cancel here. So I'm going to collect terms. I'm going to put the H2S first, and then the NH3. And then I'm going to put the RT. I really just should use a rounded bracket there because we're not talking about the concentration of RT. We're talking about RT. I'm going to put squared. See why I'm doing squared? RT, if you have it twice multiplied together, it's R squared T squared or RT squared. Okay, so now look what happens. Kc is just these concentrations multiplied together. So that's right there. That's Kc. So Kp is equal to Kc times RT squared. Now, the tricky thing about this question is, well, actually, no, it's not tricky. It says calculate Kp from Kc. Okay, so it looks like Kp is equal to Kc times RT squared. So there's your equation. We don't have to calculate the actual value. We just have to write the equation that shows how to get Kp from Kc. Okay, that's all we have to do with that one. Now let me see if there's any that are any more complicated. Oh, here's another one. I'm going to show you one more. Okay, these are kind of fun. And then we'll call it quits for this one. It's a very different kind of problem than you're probably used to doing. It's almost like a math problem, right? So again, Kp, Kc. So consider the following chemical equation. So see, it's 2PbO, that's lead 2 oxide solid plus O2 gas in equilibrium with lead 4 oxide. So these are actually like battery terminals. Solid, look at a solid and a solid, right? So how do we deal with that one gas? Well, the point is that if we're doing Kp, we just worry about gases. So these are solids, heterogeneous equilibrium. Liquids and solids, you ignore them. They make them one, okay? How do we calculate Kp from Kc, okay? Again, you're just writing out the expressions here, okay? Now, it's 2PbO solid plus O2 gas goes to 2PbO2 solid. Okay, so I'm going to do Kc first. That's a solid, so I'm going to put a 1 in. Divide, oh, that's a solid too. So I'm going to put a 1 in, and then that would be concentration of O2. Now, you don't have to have the 1 in the denominator because 1 times 10 is 10, but you do need to keep that 1 up there because if you didn't put that up there, you know, it would be difficult to interpret what that means. So we write it just as 1 over concentration of O2. Okay, so there's your expression for Kc. Now we're going to do Kp. Again, you have a product over here that's a solid, so it's just 1 over. Again, there's a solid there, and then there's your O2, so P of O2, right? So there's your expression for Kp, okay? You don't need the 1 in the denominator, but you do need it in the numerator, okay? Now, pressure of O2, okay? I'm going to come back. We want to show how to calculate Kp. So Kp equals some function of Kc. That's really what we're looking at, okay? So what I'm going to do is I'm going to, again, put in here 1 over concentration of O2 times RT, right? You know, P equals concentration of gas times RT. Sometimes you'll see this if you look on YouTube and stuff, you'll see concentration of O2 times, they'll put a C for concentration so that you have just like one letter there, okay? Now keep in mind, 1 over the concentration of O2 is Kc. So this is Kc right here. But there's also an RT underneath in the denominator, so it's over RT. Okay, now that's one way you could write it, Kc over RT, and I have no problem with that. However, it may very well be that when you're entering this into ALEKS, they may want you to write it like this. You put parentheses and you put RT to the -1. That's just another way to do it. Kp is Kc times RT to the -1, right? So, you know, just like we did with rate constants, if you had like, you know, rate constant was 1 over seconds molarity squared, this would be written molarity to the -2 seconds to the -1. If we have RT in the denominator, we can write that as times RT to the -1. And there you go. So there's 3 examples of that particular problem of the conversion between Kp and KC. So in the next video, we'll look at some little bit more challenging calculations. We'll look at some assumptions, and we'll really get into the nitty-gritty of these calculations. But this hopefully will help you with that step.